Well, hello there, wonderful class. Welcome to your exam 3 practice exam. This is one of, I think, a couple practice exams that are posted. So, all right, we're going to go ahead and start by balancing the combustion reaction of butane. This would be a very straightforward, or a very straightforward, similar question to what I would ask you in class. So we're going to start with this. But anytime you have combustion, that means you're going to add O2, and you're going to form CO2 and H2O. Again, it doesn't matter which side these guys are, which order they're in, as long as they're on the correct side of the arrow, I should say. All right, so when we balance, we want to balance the oxygen last because it's a loner pair to itself, and we can just CHO it up because it's fun to say. Okay, the left-hand side we have 4 carbons, the right-hand side we have 1. 4 divided by 1 is 4, so we put a 4 in front of the CO2. That gives us 4 carbons on each side. Moving to the hydrogen, on our left we have 10, on our right we have 2. 10 divided by 2 is 5, so we put a 5 here in front of the H2O. Last but not least, the oxygen, on our left we have 2. On our right, let's break it up. We have 4 CO2s, so each CO2 brings 2 oxygens. So if we have 4 of them, there must be 8 oxygens from this. And then from the waters, there's 5 H2Os. Each H2O has 2 hydrogens and 1 oxygen. So this would be 5 oxygens. We don't freak out. 8 plus 5 is 13. And even though it's an odd number, we don't worry. 13 divided by 2 is 6.5, or 6.5. But we know that we want to have whole number combustion reactions. So, or whole number any kind of reaction. So anytime you get something like this, it's a halvesy. You don't want to just multiply this one by 2 to get a whole number because that would just double the oxygens and everything else would be screwed up. So you want to go ahead and double the coefficient of all of these. So all of these we're going to multiply by 2. And what that does is it gives you a final answer of 2 C4H10 plus 13 O2, yielding 8 CO2s and 10 H2Os, and that would be your final answer. Cool. All right, on to the next one. In your papers, I have since added that this reaction should be there. 6 waters plus 6 CO2 forms C6H12O6, or also known as glucose, and 6 oxygens. This is the photosynthesis reaction. Okay, so now we can kind of read this. It says, the following reaction occurs in photosynthesis, and that should be the reaction. If a plant consumes 37.8 grams, what do we do with grams? Turn it to mole every single time. So the molar mass of carbon dioxide, you could add up the carbon and 2 oxygens, or I usually give it to you, is 44.01 grams per mole. Because we'll need it, I'm going to write waters down as well. It's 18.02, and again, this is usually given. But if it's not, look on the periodic table for a carbon and 2 oxygens. Okay, so we're going to start off here, 37.8. To put grams into moles, you divide by the molar mass. So the first thing I'm going to do is divide that by 44.01 grams per mole, and that gives me, let's do it, 37.8 divided by 44.01 gives me 0.85890. Remember, this had 3 sig figs, so I want to keep 3 sig figs, but have 2 extra mole. All right, so now I can read it again. If a plant consumes this many mole, what mass of water in grams would it also need? So this is going to be our question mark. It's asking about water, and we know it needs to be in grams, so it helps to write that it's grams here so we can remember. We know that this number is 0.85890 mole. Remember, we only ever put mole underneath these. And we're good to go. There's no limiting reactant. We know for every 6 moles of this, you get 6 moles of that. So it should be the same answer, but nevertheless, let's set it up as though we didn't know. So 0.85890 mole of CO2. If this is mole of CO2, we have to match it down here. We know for every 6 mole of CO2, and then we turn it into our question mark up top, which is 6 mole of water. I continued on because the question didn't ask for it in mole. If it did, we'd be done. It asked in grams. So now if this is mole H2O, we put mole down here. And it's 18.02 grams up top. That's how we're going to turn it into mole. To turn grams into moles, we divide it by the molar mass. To turn mole into grams, we're just multiplying by the molar mass. If you want to make this a two-step process, you're welcome to. And the answer I get, so the 6's cancel, right? But I could have divided by 6 multiplied by 6 times 18.02, and I get an answer of 15.477 grams, or simply, because there's 3 sig figs here, 15.5 grams. All right, moving on to ammonia. It says ammonia can be synthesized in the reaction below, and it gives you the reaction, and then it gives you all these masses. So in this case, this is how it should be. You get a reaction, you get the masses. It says if you react 86.3 grams of NO, we know the first thing we're doing before we even have to worry about the question, let's turn that sucker into mole. NO has molar mass of 30.01 grams per mole. So for our NO, 86.3 divided by 30.01 gives me an answer of, oh, that is not right. 86.3 divided by 30.01 gives me an answer of 2.8757 mole, and that would have 3 sig figs. This was to do with NO, so our NO right here was at 2.8757. All right, with 25.6 grams of H2, boom, divided by 2.02 grams per mole, because that was given to us here for the H2. Okay, and I get an answer of 12.673 mole. 12.673. And it wants to know the theoretical yield of NH3 in grams. So there's our question mark, and it needs to be in grams. All right, so zoom in a little bit just in case you can't see it. All right, so we know our mole here, we know our mole here, we have a question mark over here. If you remember, that means we gotta find the limiting reactant first before we can figure out the theoretical yield. So I'm gonna divide this number by 2, and I'm gonna divide that number by 5. I can tell right away that this one's gonna be my limiting reactant, because 12.6 divided by 5 would give me more than 2, and 2.8 divided by 2 would give me less than 2. So I kind of know right away that this is my limiting reactant, but go ahead and do it in your calculator if you need to make sure. But once I find my limiting reactant, right, we kind of cross these suckers out. And I've set myself up for success now. I know my limiting reactant amount has to go here. So I've got 2.8757. And that's mole of no. If that's mole of no, we know mole of no has to go down here, but it's got a 2 with it. So for every 2 mole of no, we get 2 mole of NH3, which is where the question mark was. Now we would be done, but again, it asked for it in grams. So just like we did in the previous question, you simply multiply it by the molar mass. We do that because we know a mole of NH3 has a mass of 17.03 grams. So let's go, I was looking to see if I can get it, but all right, so let's do this. 2.8757. I know the 2's cancel, they're both 2's. And then I'm just gonna multiply it by 17.03. Whoops. 2.8757 times. And I get 48.97 grams. Remember, this had 3 sig figs, infinite 4. So now my final answer needs 3. We don't just pretend that that 7 doesn't exist. We round up. If you got $48.97, that means you got $49. And we have to make it 3 sig figs, so we add 0. All right. Moving on. Just to remind you, what we found was the theoretical yield. Now it says you recovered 27.3 grams of NH3 from the reaction. What is a percent yield? Well, if you recovered that much, this is therefore our actual yield. To remind you from the previous page, our theoretical yield was 49.0 grams. Actually, I'll use the unrounded number, 48.973 grams of NH3. Here it's saying that our actual yield is 27.3 grams NH3. Now you could turn these both into mole first, or because they happen to be grams and grams, NH3 and NH3, you're comparing French fries to French fries. So it's okay to keep these. And then you're simply going to multiply it by 100% to get your answer. Okay, so 27.3 divided by the last answer, and then times 100 gives me 55.7%. That had 3 sig figs, that had 3 sig figs, so my final answer is 55.7% for the percent yield here. All right, moving on to solution concentration, just to kind of remind you how that works. It says, what is the molarity? If you remember, molarity is mole over liters, and sometimes it's written as big M, which we know anytime you have a big M, you cross it out, and you write mole over liter. Okay, it says, what is the molarity of a solution containing 27.6 grams? Grams, boom, boom. The molar mass of NaCl equals 58.44 grams per mole. It's the mass of a sodium and a chlorine. All right, so grams in a mole, we divide by the 58.44 grams per mole. Let's do that. 27.6 divided by 58.44, and I get an answer of 0.47228 mole. All right, so that's the number of mole we have. Again, we're looking for molarity. Molarity is mole over liters. We have the mole. Do we also have the liters in the problem? We sure do. It's right there, 1.1. So the way to get the units of mole over liter is to simply take the number of moles. It would have 3 sig figs, and divide it by the number of liters. And I get an answer of 0.429, or with 2 sig figs like it should have, 0.43 mole per liter, because this one had 2 sig figs. All right. Now we move on to this one, how many liters? So here it's asking for volume. Anytime something asks for volume, you're probably going to divide something. But let's read through it. How many liters of a 0.135 big M, we know that that's actually mole over liter, solution contains 1.6 mole. So this is a a dimensional analysis problem. This is one you did in your very first week. We have something with 2 units. Let me rewrite the numbers real quick. We have 0.135 mole per liter, and we also have 1.6 mole. If I did this thing, you know what's going up here would be the 1.6 mole because it's got just 1 unit. If that's mole, mole has to go down here, so we're going to take this 0.135, take it with it, and we're left with liters. That's the way moles cancel, and you're left with liters. So we just take 1.6, and we're dividing it by 0.135. I'm going to do that again because that doesn't look right. Oh, yep, I got an extra point. 1.6 divided by point. Oops, I did it again. I'm going crazy. 1.35, no. Sorry, I got distracted. Somebody outside just started a lawnmower. All right, perfect. And I get an answer of 11.852, or it would have 2 sig figs, 12 liters. So hopefully this actually makes sense. I probably should have spent some time making sure that you understood this. If it's a 0.135 mole per liter solution, that means 1 liter of it only has 0.135 moles. So if we have only 0.135 mole in this liter, how many of these do we have to add up in order to get a whole 1.6 mole? Quite a few. Well, actually, apparently 12. Okay, on to solubility. It says, which of the following is soluble? So here, that's where you're going to use your solubility chart. It's very helpful if you memorize some of it, all of it preferably, but it'll be given to you on the exam. So it says, which of the following is soluble? Remember, you kind of look at both. You got a lead and you got a chloride, and you look and see what you see first. I see chloride first. I see it right here. So chloride is normally soluble. It's in this, everything up here is normally soluble. Everything down here is normally insoluble. But these are the exceptions where they're the opposite. So here I've got chlorine, and it says, hey, it's normally soluble. So I'm thinking, hey, maybe this thing's soluble. But when I go over here, it said, unless it's compared with lead 2, then it's insoluble. So this one would be a solid, and this would be insoluble. Then we go to barium sulfate. Sulfate's right here, SO4 2 negative, and it's normally soluble, so I'm all excited too. But then I walk over here and boom, with barium, the resulting compound is insoluble. That means it's not going to be soluble either. This is an insoluble, and it will be a solid. Then we get to the copper 2 chloride. Hey, we recognize chloride. We know chloride's normally soluble, but here it's paired with copper 2. So you go over here, is copper 2 one of these things? It is not, and that's good. That means in water, this would have been aqueous, and it would be soluble. And that's why C is our answer. Ooh, this looks fun. All right, cool. So a lot going on in this problem here. This is very similar to how I might ask a final exam question, just so you know, where it's got multiple points, making sure that you remember things all throughout the semester. So let's go ahead and get started. Before I even read anything, I see liters and mole per liter. Do y'all remember what you do with that? Just like you take grams and turn it into mole, you take liters and mole per liter, you multiply them and turn them into mole. Okay, so that's the first thing I'm gonna do. So I got 0.15 times 0.225, and this gives me 0.03375 mole of potassium chloride. It also might help here to write what potassium chloride is. Potassium chloride is KCl. That's because K has a positive charge, Cl has a negative charge, and you just need one of each. Let's move on to this next one. We have 0.15 times 0.115. And I get an answer of 0.01725. And this last one would have had 3 sig figs, and this one would have 3 sig figs as well. And it's lead 2 nitrate. Just to remind you, I'll write it up here. Lead 2 is Pb with a 2+ charge. Nitrate is NO3 with just a 1-. So we need 2 nitrates to cancel it out, and that's why lead 2 nitrate would be Pb. Put that nitrate in parentheses and put a 2 on the outside to indicate that you want 2 of them. Okay. Now it says they react in a double displacement reaction. So the actual reaction for the double displacement would be KCl plus Pb, NO3, the 2. Now if you remember, essentially in a double displacement reaction, just these things are going to switch. So it's potassium chloride and lead 2 nitrate will make potassium nitrate and lead 2 chloride. Potassium nitrate would be KNO3. And lead 2 chloride would be PbCl2. So if you weren't able to do that relatively quickly, you got to go back to naming because it's the most important thing. We've said it all semester. All right, now if you go to balance it, you'll see here I have kind of left to right, 1 potassium, no big deal. 1 chloride, 2 chlorides, something to think about. 1 lead, no big deal. 2 nitrates, 1 nitrate, something to think about. So you need essentially some more nitrate. So let's get rid of this Gary 1 first. If I have 2 over here, I'm going to put a 2 in front of this. And then over here, I had 2 chlorides, so I need to put a 2 in front of that. And now it should be balanced. All right, the other thing to consider in double displacement reactions is you want to oftentimes look at what's solid or aqueous. So potassium is one of those that we talk about and say, make sure you just memorize it, because potassium, sodium and potassium, lithium, ammonium, nitrate, and acetate have no exceptions. They're always soluble, so they're always aqueous, which means this potassium here is going to absolutely be aqueous. This lead nitrate, I just said nitrate, is always aqueous. Nitrate again with potassium, definitely aqueous. And then we get to this lead 2 chloride, which we did on the previous page. Right, we determined it was insoluble. So we did that by looking at the chloride here, and then looking over here and seeing that when it's paired with lead, it's a solid. Okay, so this is our overall reaction. It says, what is the net ionic equation? The net ionic equation, remember, you look for the solid, or the non-aqueous thing. That's aqueous, that's aqueous, that's aqueous, this is non-aqueous. And you write it on one side of the reaction. Then you draw an arrow to it and you say, what did you need in order to make lead 2 chloride? Well, you needed lead 2. And you needed 2 chlorides. And that would be the net ionic equation. The spectator ions are the other things that you didn't underline in this product over here. You had potassium and nitrate. Those guys didn't do anything, or gals. So we got potassium and nitrate. All right, now we can move on to the fun part of the equation, I think, or the question, which is, what is the theoretical yield of the lead 2 chloride? So it's asking for this right there. We know, because we started off, that underneath the potassium chloride would be 0.03375. And we know that underneath the lead 2 nitrate would be 0.01725. And our question marks over here. We've done probably 100 of these at this point, and maybe that's an exaggeration, probably 20 of them at least. And so we know what to do. The first step is find the limiting reactant. So if I divide this one by 2 and I divide this one by 1, you will find out that this one's slightly smaller. Okay? In fact, I'll do it real quick, just because you almost have to do this one just to make sure. I get 0.016, and this is 0.017. So this one's smaller. This is my limiting reactant. So when I go here, for my theoretical yield, I'm taking my limiting reactant amount, 0.03375, and I don't get lazy, I write mole of KCl. All right, now once I've done that, I'm set, because if this is mole of KCl, I know I must put 2 mole of KCl here. And for every 2 mole of KCl, my question mark was over here at the lead, I get 1 mole of the PbCl2. All right, so this gives me an answer of 0.016875, and it would have 3 sig figs. And again, this is mole of PbCl2. All right, now though, it says if 3.2 grams of precipitate is recovered, what is the percent yield? To remind you, precipitate is the solid thing. In other words, in this case, it's PbCl2. So we can take our 3.2 grams, first things first, turn it into mole. Man, I did a horrible job providing molar masses on this. PbCl2, I just kind of have it memorized at this point, is 278.1 gram per mole. So when we got the 3.2 grams of precipitate, again, the precipitate told us that it was a solid. The only solid thing is the lead 2 chloride, so we know that that's what it was talking about. So 278.1 grams in a mole. Let's go ahead and figure out how many mole that is. And I get an answer of 0.011507 mole of the lead 2 chloride. Okay, so now we can kind of read this again. If this much of the precipitate is recovered, what is the percent yield? It said is recovered. What does that make this number if it was recovered? It's the same as like saying is obtained, is made, is found, is yielded, etc. This is your actual yield. If you remember up here, we solved for our theoretical yield, and it's always going to be this way. The actual yield almost always is in the problem itself, and the theoretical yield, you find the limiting reactant, match, solve it every single time. So we know our actual yield, we know our theoretical yield, therefore, we can find the percent yield. Because we know percent yield equals actual over theoretical times 100, or 0.011507 mole of PbCl2. Write the mole in the PbCl2 so you can make sure that it matches the one you did up here, which ended up in mole PbCl2. And then times 100%. And when I multiply it by 100, I get an answer of 68%. That one would have had 2 sig figs because it was 3.2 grams. The other one had 3, if you remember. And so 68% would be our final answer. Okay, so electrolytes, it depends on the class, but I expect we'll go through electrolytes for sure. But even if we don't, it all comes down to this, that a strong electrolyte is 2 things. It is either an ionic compound, any dissolved ionic compound, meaning it must be aqueous, or a strong acid, and these are the 6 strong acids that you just have to memorize. Okay, so it's either going to be any ionic, which if you remember, that's a metal plus a non-metal, or one of those strong acids. A weak electrolyte is a weak acid. So we know acids are things that start with H. If it's not on this list, it's going to be weak. Okay. So let's go through, and then a non is nothing of neither of those. So let's look. Which of the following would conduct electricity the best? In other words, be the strongest electrolyte. Let's go through it. The first one is HF. This starts with H, so this is an acid. You should even know how to name it. It's hydrofluoric acid. Doesn't hurt to review that. Is hydrofluoric acid on this list? Hopefully you agree it is not, and because of that, it must be a weak acid. If it's a weak acid, it must also be a weak electrolyte. As indicated here, any weak acid has to be a weak electrolyte. Let's move on to the next one. C12H22O11. These are all nonmetals. If they're all nonmetals, that means they're not an ionic compound. I don't see this sucker starting with an H. This is a non-electrolyte. We get down here to NaF, sodium fluoride. It doesn't start with an H, but we know sodium is always aqueous. It's in that chart. And if sodium's always aqueous, then that means it's a dissolvable ionic compound. This is a metal, that's a nonmetal. And therefore this, any dissolved ionic compound, would be a strong electrolyte. But just to make sure, let's move on to the next one for some extra practice. Here we have H, C2H3O2, which you should know is acetic acid. It's an acid made out of acetate. Starts with an H, and that's how you would know. And then you look on the list that you will have memorized and say, is acetic acid on that list? The answer is no, and therefore this is a weak acid, which makes it a weak electrolyte. So your answer is C. All right, so hopefully that helps. Here's the topic list. Make sure you go through and you understand these things and you have a strong, a strong grasp of them all, and you'll do just great. All right, y'all, have a great day. Bye.